Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, and welcome to Week 3, Lecture 1 of Dynamic Atomic Force Microscopy Methods. In Week 2, we had gone over many analytical aspects of dynamic atomic force microscopy. We acknowledged the fact that when you try to understand the meaning of images that you get in dynamic AFM, you need to have a model to really understand what's happening at the tip-sample interface, because we observe the tip-sample interaction physics through the effects that it has on the oscillator. In the last week, we tried to get as far as we could using analytical methods. We realized that the equations were complicated, but we tried to proceed as best as we could to try and understand the general behavior of the probe as it interacts with the sample. Towards the end of the second week, and especially in the last lecture, when we were discussing average and peak forces, it became apparent that when one goes to peak forces, one already has to start thinking about doing numerical simulations of the entire probe interacting with the sample through these different tip-sample interaction forces. Some of the key results from last time, based on analytical techniques, were that the average force exerted by the tip on the sample during a cycle of oscillation, interestingly, does not depend on the local material properties of the sample. In other words, you could have a situation where if the tip is tapping on a soft material, and if this were time, the tip-sample interaction appears as a pulse as the tip taps the sample in time. For a soft material, the contact time would become larger and the peak force would become smaller. And for a harder sample or a stiffer sample, contact time becomes narrow and the peak force becomes high, in a way that the average force still remains the same, as long as you're using the same cantilever and you're operating at the same amplitude far from a sample and same amplitude reduction. This theory, of course, was an analytical theory that was based on the assumption that the contact time is a very small percentage of the overall time period of the oscillator. Nonetheless, it provides us some interesting guidelines of how to think about average forces and their dependence on operating conditions. Towards the end of the last class, we started talking about peak forces and the effect they could have on the sample, and the fact that the peak forces are typically much larger than the average forces. And it becomes very hard to try and understand what the peak forces are without the help of simulations. And we did show a comparison between analytical approximations and simulations, and basically proving the fact that in tapping mode, at least as you come close to the sample, the peak forces can be as high as 10 times more than the average forces, but they tend to, as you approach the sample, increase in magnitude and then go back down again, reaching a maximum value somewhere between 50 and 60% of amplitude ratio. So we also talked about the fact that you might actually get some scaling laws that allow you to relate peak forces to local properties, local van der Waals forces, or local elasticity, and so on. But what we're going to move to this week is we're going to move on to doing numerical simulations of the full equations, the point mass oscillator model interacting with tip-sample interaction forces, and we're going to use VEDA for it. Why use numerical simulations instead of using the analytical tools? There are many reasons why. Analytical tools are great to give you an overall sense of the physics that's involved, but at the end of the day, if you want to scan a sample and get some really realistic insight into what's happening for your particular sample, you really need to go to numerical simulations. So all of you are probably already registered on nanohub.org on VEDA, which is a virtual environment for dynamic atomic force microscopy. Those of you who've taken part 1 have gone through VEDA, but for the benefit of those who haven't, I want to quickly reiterate how you access the tools and how you navigate through the layout of the graphic user interface. So to register on nanoHUB, you need to go to www.nanohub.org. The web address is given, and create an account for yourself and log in. And once you log in, to get to VEDA, there are 2 steps. You first choose to go to Resources, as shown. And then once you have Resources, you need to go into Tools. And under the Tools, you're going to find tools for atomic force microscopy, and then the drop-down window comes up with a list of tools, of which you want to choose VEDA 2.0, which is the version 2.0, and then you would launch the tool. So when you launch the tool, you get this particular interface. You have this nice image of a cantilever oscillating, and then you have a pick a tool window bar that comes in, and if you put your cursor on that, you get a drop-down menu of all the different tools that you can access using VEDA. As you can see, the first tool is the tip sample viewer. This allows you to access one of the 19 different tip sample interaction models that are built into VEDA that you can pick and choose and play around with parameters to see what the force versus D, tip sample distance, model is for different interaction forces. Then you also have force distance curves. These are static force distance curves, snap in, pull out, and so on, that you can do on a variety of different materials. There's something called the jump mode, which is related to force volume-like techniques. And then you have contact mode imaging, which you did study in part 1, especially with its relevance to how to choose feedback control parameters while scanning. And then you see this very long list which goes through frequency modulation techniques and so on. I just want to bring your attention first to amplitude modulated tools, which is basically tapping mode. And you'll see that, broadly speaking, these are divided into 3 categories. There is a basic approach, dynamic approach curves tool, which is what we're going to talk about today and in the next lecture. And there is a scanning tool, and again, there's a basic and advanced version of all these tools. So in this particular course, we're going to focus on using the basic tool. The advanced tool is used for when you want to do multi-frequency approaches, you want to do simulations in liquids. There are many additional parameters that need to be adjusted, and so that'll be out of the scope of this particular nanoHUB-U based course. So we're going to go ahead and choose amplitude modulated approach curves, tapping mode approach curves, the basic, which is to be used for ambient or vacuum conditions. And in order to walk you through an example solution, let's take a look at what the problem is that we're going to try and solve. The problem is going to be a typical tapping mode cantilever. Let's say the spring constant has been calibrated to 40 Newton per meter. The Q factor, which remember you can get from the thermal tuning or from direct tuning of the cantilever, and the natural frequency omega naught, or F naught in this case, which is given in hertz, 350 kilohertz. And you're given that the amplitude far from the sample is 30 nanometers. The tip has a nominal radius of 20 nanometers. The Young's modulus of the tip is 130 gigapascal. And there's a sample, that you're going to be approaching. And the sample is a soft polymer with a Young's modulus of 1.2 gigapascal and a Poisson's ratio of 0.3. It's also important to note that for this particular simulation, we want to have the excitation frequency omega being exactly equal to the natural frequency omega naught. Now, in this particular case, we're suggesting that you choose this is not a very adhesive sample, so we will go ahead and choose the DMT interaction model, which is sketched out on the left. You have a generic attractive gradient due to Van der Waals forces, and then you have an elastic repulsion. And the Hamakrup constant value for this combination of let's say it's a silicon tip, and the sample is a typical polymer sample, is generally of the order somewhere lies between 5 to 10 times e to the minus 20 joules. So this is a typical number, and just for it's a good question to ask what number should be put into this model for the simulation. But broadly speaking, for a whole bunch of materials, unless you can find data for the Humbucker constant, you're probably going to be fairly reasonable in guessing a number of the order of magnitude of 10 to the minus 19 or 10 to the minus 20. And then there's a certain value of adhesion that you can choose. This would be, if you were to do a static pull-off curve, what would be the value of the minimum adhesion force required to pull out the tip from the surface. When you put it all together, you would like to solve this and answer the following questions. How does the amplitude phase of the oscillator change as you approach the sample? How does the indentation change? Remember, all you observe in a dynamic AFM experiments are the changing amplitudes and phases. What you don't, or what's hidden from you, are things like peak forces or how much indentation you're causing dynamically as you tap on the sample. So, what's the mean indentation, what's the mean interaction force, and how does all this change as a function of z as you approach the sample? The other important question we want to ask is there a difference in all these quantities as you're approaching the sample versus when you're moving away from the sample? Keep in mind that for this simulation, we're not including any dissipative components in the tip-sample interaction. It's purely a conservative interaction model based on the DMT contact mechanics idea, which was discussed in part 1. So what one does here is we have made things a little easy for a starting user to use in VEDA by providing a lot of worked out populated examples where all the parameters have been pre-populated for a certain set of operating conditions. So if you go to the drop-down menu on the example loader and pick out example 1, this is going to be amplitude and attractive and repulsive regimes of oscillation. So when you choose that, all these parameter values relevant to this problem are automatically populated in all the key locations. Now, what I want to bring your attention to is the very top sequence of windows that you're going to go through. Right now, on the top left, window number 1 is highlighted. This is operating conditions and cantilever properties. Following which, after these things are filled out, you go to the next. You can click on number 2, which is tip sample interaction properties. Number 3 is simulation parameters. And number 4 is basically, when you click on it, it simulates the probe as it's approaching the sample. So here's where, in this particular page, all the operating conditions and parameter or cantilever properties are populated. Then you move on to the next window, which is tip sample interaction properties. Now, as I said, the choice of DMT interactions and all the parameters associated with them are already put in place, but you absolutely have the possibility of actually changing things or choosing a different tip sample interaction model as you see fit. And then the simulation parameters are described in more detail in the manual that you can access from VEDA. For the moment, we recommend to just go ahead with the default values. The simulation parameters are things like conditions and what time steps you need for simulation, and what tolerances and so on. So those are details, but for these example simulations, we all have them preset to good default values. So when you hit the simulation, what will happen is the code will compile on the cyber infrastructure. So the computer code VEDA is not running on your local computer. It runs on the cloud computing infrastructure of the nanoHUB, and then in a few seconds it'll return to you this solution. As you can see, what's plotted out here is the amplitude of the oscillator as a function of z distance as you're approaching the sample. And you see some very interesting things. You see that at large z distances, the amplitude remains fairly constant. As it starts interacting with the sample, the amplitude starts decreasing. And then there's a slight jump in amplitude. And then the amplitude continues to decrease again. You can choose to study also what happens when you retract from the sample. And if you choose to retract from the sample, you can just go down to example number 2, which is the retraction curves. And this has already been pre-populated with exactly the same parameters as in example 1. It's just now going to retract from the sample. As you go ahead and do that, you would get the following response. And you can actually, once you do 2 different simulations for approach and retraction, you can display them together on the same window. And by selecting, there's a bar at the bottom. It says simulation number. So if you click on all, which is a little tab on the bottom left, it displays all the simulations you did, or you can select toggle between the different simulations you've done by choosing 1 or 2. What you see here is a very interesting effect that we already talked about in the last week when we did analytical approaches, in that when you approach and retract from the sample, there's actually a range of z values where there are 2 different oscillation states with the same amplitude that coexist. And we talked about this and how this could lead to instabilities, especially if you choose as amplitude set points those amplitudes that can be achieved at 2 different z distances. In addition to the amplitude of the oscillator as you approach or withdraw from the sample, if you go down to the result menu, there's a whole bunch of different ways, different properties or different features that you can plot. You can select the phase, for example, and what you see is as you approach the sample, you follow the green curve, where initially the phase starts increasing above 90 degrees, and if you'll recall, when the phase increases above 90 degrees, the virial is actually positive, and the tip is oscillating in the attractive regime of oscillation. On the other hand, when it transitions to the repulsive regime, it's experiencing net repulsive tip sample force gradients, and the phase lag drops to below 90 degrees. So you can see this in the simulations, and you clearly see there's a transition at some point. It jumps from the attractive to repulsive. The analytical method was not able to tell us what are these points at which the oscillator is going to jump, at what z distance is going to jump from attractive to repulsive. All the analytical approach did was to tell us that it is possible for, under the correct operating conditions, for 2 oscillation states with the same oscillation amplitude but at 2 different z values. Upon retract, we see again that the jump, the hysteresis that we were observing in the previous graph in the amplitude, is due to the fact that the tip on withdrawal jumps up to the attractive regime. The phase of it jumps up, so it moves to the attractive regime of oscillation a little earlier, creating this hysteresis. Another, hidden quantity that you can get out of these simulations, which you could not get through just simple experimental measurements, is the indentation. So if you go to the result tab and click amongst the different, results you can plot, indentation is one of them. And what you notice is when you first come into the sample, the maximum indentation rises very suddenly. It reaches quickly a nanometer and a half, and kind of then plateaus out a bit and then keeps down a little bit. And when you withdraw from the sample, you follow the same peak forces, or same indentation, until you jump into the attractive regime of oscillation. Another important hidden quantity that you can detect using simulations is the history of tip sample interaction forces. So when you're choosing your simulation parameters and your operating conditions, there is a choice that asks you whether you want to plot the time history of tip sample interaction forces and the time history of oscillation. Now keep in mind that the entire oscillation that we had, this cantilever oscillating at a high frequency and approaching the sample, there were literally thousands of cycles of oscillation as you approach the sample, and all the simulations were done within a few seconds. So it's very hard for us to store the entire history of tip sample interaction forces as you approach a sample. So instead, when you go to the operating conditions, we actually give you an option that when the simulations are finished, we can actually keep the time history of tip oscillations and the tip sample interaction forces, not at every point during the approach curve, but we have the user specify which set point ratios or which amplitudes are those, at which you want to see this time history. So when you loaded this example, it was automatically populated. The parameters choice were already populated to allow the user to look at the history of tip oscillation and tip sample interaction forces at a set point amplitude ratio of 0.55. So when you click on that and display the results, it shows you that not in the entire approach curve, but when the amplitude had decreased to 55% of its value far from the sample, this is how the tip would be oscillating. Shown in blue, you find a beautiful, nice sinusoidal profile. In spite of the fact that you're actually interacting with the sample at the very bottom of the curve, it still takes a very sinusoidal curve. And this was important because when we were doing the analytical theory, we assumed that the motion would continue to be sinusoidal even while interacting with the sample. The simulations do show that this is indeed the case. So what we find is when the tip swings to the bottom end is when it's interacting with the sample, and on the same time axis, we've plotted here the tip sample interaction force history, which is in green. What you find is as the tip is coming towards the sample, the interaction force actually becomes negative, indicating attractive forces. So the interaction force is pretty flat and then becomes attractive. When it goes a little deeper, the tip goes a little deeper, the interaction force becomes repulsive, and then the tip moves away from the sample, the force drops, and then you have the last tail of the attractive forces. So you get this typical characteristic pulse of tip sample interaction force as a function of time that comes up as a result of these simulations. And with that, I hope you've got a nice introduction to how VEDA can be used to understand dynamic approach curves, and how it can be used to plot the different hidden quantities, indentation, peak forces, and average forces and phase and so on, and allows you to play around with different tip sample interaction forces to understand the effect they have on, for example, bistability, or on phase, or on amplitude reduction. Thank you.